Last time we talked about covalent bonding, which was two nonmetals bound together, and we used those great prefixes. Today's type is ionic bonding, and it's a metal and a nonmetal. So instead of two things from the right of the staircase, you're going to have something from the left of the staircase with something from the right of the staircase. An example would be like sodium chloride. So you have a metal over here from the left with a nonmetal over here from the right, NaCl. And for the most part, it's pretty straightforward. You simply name them. It's sodium and chloride. It's still going to end in IDE. But if you'll notice, there's one little trick to the ionic ones. There's no prefixes. What you have are the charges. Sodium, if you look to the top of it, there's a +1 for all these things, hydrogen all the way down to francium. For chlorine, the charge is -1, and it applies for fluorine, chlorine, bromine, iodine, and astatine. All the way down to the staircase is -1. So if you're binding sodium and chlorine, it's +1 and -1. And what you're doing is you're balancing the charges. Since sodium is +1 and chlorine is -1, they are happy when there's only one of them, one of each. So +1 sodium and -1 chlorine is all balanced out in neutral. So the formula is NaCl, 1 sodium and 1 chloride. And I'll show you how to systematically do that for all of them. Okay. So just as an example here, if I were to ask you to write the formulas for these things, sodium chloride, potassium bromide, magnesium oxide, magnesium iodide, all these all the way down to beryllium fluoride, you might immediately say, well, NaCl, KBr, again, you have to start to learn the periodic table. Potassium symbol is K. Well, that's because its Latin name starts with a K. Magnesium oxide, you might say MgO. Magnesium iodide, Mgi. Aluminum phosphide, AlP. Calcium fluoride, lithium sulfide, and beryllium fluoride. And for the most part, that's right, but some of these are wrong because it's the charges that dictate how many of each. Remember I said that there was 1 sodium and 1 chlorine because they're +1 and -1? If you look at the periodic table, sometimes things have charges of 2, +2, or +3, or -3, or -2. So in reality, some of these things, it's not as straightforward. For magnesium iodide, magnesium, if you look on the periodic table, has a +2 charge, where iodine has a -1. So it's going to take two -1 iodides to balance the +2 magnesium. The same for calcium fluoride. Lithium sulfide, lithium is +1, sulfide is -2. Beryllium fluoride, +2 beryllium, -1 fluoride makes it BeF2. The systematic way of doing that is called the crisscross method for a metal and a nonmetal, an ionic compound. Remember, it has to be something from the left of the stair step with something from the right. Covalents are both from the right, and there's no charges involved, just prefixes telling you what's there. Okay, so an example, calcium chloride. Well, the crisscross method says that step 1, you write the symbols, CaCl. Step 2 is you write the charges above them, Ca +2, Cl -1. Then you cross the numbers down. You take those charge, not the plus or the minus, just the magnitude. The 2 from calcium becomes the subscript for chlorine, and the 1 from chlorine becomes the subscript for calcium. And you sometimes have to reduce, or if you can reduce, you reduce, and you don't write ones. So calcium chloride isn't just CaCl, it's CaCl2. And this should make sense because calcium is +2 and chloride is -1. So it's going to take 2 -1 chlorides to balance 1 +2 calcium. So it's symbols, charges, cross them. Another example, ammonium oxide. Ammonium isn't an element, it's what's called a polyatomic ion, a mini atom ion, and you'll learn those next class. So ammonium is NH4 and oxygen is O. That's the symbols. You write their charges. NH4 is a +1. It's actually down at the bottom of your periodic table. There's lists of polyatomic ions. They're down there. And ammonium is NH4 +1. Oxygen, if you look above it on the periodic table, is -2. So it's symbols, charges, cross them. NH42O1. Well, okay, so it's plus 1 ammonium and minus 2 oxygen, so you need 2 ammoniums to balance the 1 oxygen. But if you look at it the way it's written, NH42 and O1, that really doesn't make a lot of sense. This looks like there's 1 nitrogen, 42 hydrogens, and an oxygen. You just have to think mathematically. This is all about numbers. If you think about back in math, if you want this 2 here to apply to the entire ammonium ion, what do you have to do mathematically? Right, some of you are thinking, yeah, you got to put parentheses around it. If you have a polyatomic ion and you have more than one of them, in this case we have 2, you have to put parentheses. That 2 needs to tell me that I have 2 ammoniums, not 42 hydrogens. So it's still symbols, charges, cross them, but sometimes you have to put parentheses if you have more than one polyatomic ion, and reduce. But here you don't reduce the 4 and the 2, you only reduce the numbers you brought down, which are 2 and 1, so those are already reduced. So that's writing formulas. Naming ionic compounds, remember, it's a metal and a nonmetal. That's how you recognize what it is. Something from the left of the stair step with something from the right of the stair step. The problem with naming the compounds is, here, NaCl, you can certainly call that sodium chloride. That's great. And FeO, well, okay, iron oxide ends in IDE. Fe2O3, iron oxide. FeO2, iron oxide. Obviously, there's a problem. You can't just call all of these 3 things here iron oxide because they're different. This is 1 iron and 1 oxygen, 2 and 3, 1 and 2. They're different things. They have different masses, different characteristics. You can't call them all by the same name. How we do this is with their charges. We're going to write their charges down in the name, but we're going to use Roman numerals to write the charges, and I think most of you know the Roman numerals. But here, the thing is that here, in this group 1, it has a +1 above it. All of these are +1, always. In group 2, always +2. Boron in group 3 is +3. In group 4, they're either plus or -4, -3, -2, and -1 for this group from fluorine down to astatine. But for all these things in blue here, the transition metals, the problem is that they form various charges. That's why there isn't a charge written above them in the periodic table. Iron can be +1, +2, +4. Copper can be +2 or +4. Nickel can be +1, +3, +5, +7. They all have various charges, but you'll be able to figure it out with a little bit of basic second-grade math, because you always know what the negative thing with the nonmetals charge is. You can figure out what the positive things, what the metals charge is. The solution is here. FeO. You know from looking at the periodic table that oxygen or oxide's charge is -2. Well, it's a balancing act. If there's one Fe and one O, that means they have the same charge. Since oxygen is -2, the one lone iron must be 2 also. So this one is iron 2 oxide. Next one, Fe2O3. Okay. You'll know that oxygen is still -2. But there's not just one of them, there's 3. So 3 -2 oxides totals -6. Well, so if the negative side is -6, the metal side, the positive side, must be +6 to balance it out. And I know that I have 2 irons totaling +6, so it must be iron 3 oxide. I know, it's a little bit, but you'll get the hang of it. FeO2. Okay, there's 2 oxygens. I know that each one of them is -2. So 2 -2 oxygens is -4. To balance that out, the one iron must be +4. So iron 4 oxide. You notice we're not calling them all iron oxide. We're giving the iron's charge because that tells us what the real formula is. Okay? And again, if you would like to write these down, if you don't know all the Roman numerals, write them on your periodic table. You don't have to memorize them. You just have to know how to use them. I suggest you write them somewhere in the top center above the transition metals, which is the ones you'll use them for. So it's IV, all the way down to X for 10. And you don't need to know more than 10. So remember that ionic compounds are a metal plus a nonmetal. So MgBr2. If we want to write the name, well, we're simply going to write the names. The metal always comes first, magnesium and bromine. They're real simple to write the names. You have Mg, magnesium, you have Br, bromine. But remember that the second word, the anion, the negative thing, always ends in IDE, unless it's a polyatomic ion. So it becomes magnesium bromide. So write the names, and the second one with IDE. And then if it's a transition metal, if it's one of those metals in the middle of the periodic table, you must write its Roman numeral charge. But if you look at it, magnesium isn't in the middle, it's in that group too. It's always +2. It never forms anything other than +2. So the name of MgBr2 is just magnesium bromide. Another example, FeBr. We did this one, but I just want to illustrate again how to do this. You can't call all of these things iron bromide, okay, because they are different. The first one has 1 iron and 1 bromine. Then it's 1 iron and 2 bromines, 3, 4, 7. They are different things. They need different names. The first one is iron 1 bromide. You know it's 1 because bromide is -1. So it is balanced by a +1 iron. For the second one, Br2, there's 2 -1 bromides. That means iron must be +2 to balance it out. The third one, Br3, 3 -1 bromides must be balanced by a 3+ iron. A 4+ iron balances the 4 bromides, and a 7+ iron balances the 7 bromides. If it's a transition metal, you must include the charge in Roman numerals for the metal. Just to work that one out, FeBr2, iron bromine becomes iron bromide. You need the charge. You know bromide is 1. There are 2 of them. That's a total -2 for the bromides. Iron must be +2. Okay, just nice, simple, straightforward way. Iron bromine becomes iron bromide because you just end it in IDE. That means it's in a compound. It's 3 -1 bromides, so iron must be +3, iron 3 bromide. Iron bromide for FeBr4 must be iron 4 bromide. One more example because I think these just take practice. Cobalt is a transition metal. It's in the middle of the periodic table. And sulfur, so cobalt sulfur, but remember the second one just simply ends in IDE. So cobalt sulfide. You don't know cobalt's charge because it forms multiple charges, but you can figure it out. You know that sulfide, if you look on the periodic table, right below oxygen, has a 2- charge. There are 2 of them in this. So 2 -2 sulfides is a total of -4. So that -4 charge must be balanced by a +4 cobalt charge. So it's cobalt 4 sulfide.